Hi everyone and welcome to our A-Level Computer Science series. Today we're diving into the fascinating world of the components of a computer. This is Unit 1, where we'll explore the key parts of a computer and their uses. Let's get started. Right, we're going to kick things off with an overview of what we'll be covering today. We're going to look at the main components of a computer's processor, understand their roles, and see how they work together to execute instructions. Now, this is fundamental knowledge for anyone studying computer science. So by the end of this lesson, you'll be able to explain the roles of the arithmetic logic unit, or ALU, and the control unit. You'll also understand the fetch execute cycle and the functions of key registers like the program counter, accumulator, memory address register, memory data register, and the current instruction register. These are the building blocks of how a computer processes information. The CPU, often referred to as the brain of the computer, is made up of several key components. These include the control unit, buses, the arithmetic logic unit, and dedicated registers. Each of these components has a specific role to play. Think of the CPU as a chef in the kitchen. The control unit is like the head chef who directs the other chefs. The ALU is the chef who chops and cooks, and the registers are the small bowls that hold ingredients temporarily. The control unit is responsible for directing the operations of the processor. It sends signals to the other parts of the computer to ensure everything works in harmony. Buses are the pathways that transfer data between different parts of the computer. They can be thought of as highways that carry data to and from the CPU. The ALU performs all the arithmetic and logical operations, such as addition, subtraction, and logical comparisons. Finally, the registers are small, fast storage locations within the CPU that temporarily hold data and instructions. The control unit is crucial because it manages and coordinates the activities of all other components in the processor. It sends control signals via the control bus to other parts of the computer. Imagine the control unit as a traffic cop who directs cars, such as data, to ensure they move smoothly and efficiently through intersections, which can be components. Without the control unit, the processor would be like a chaotic kitchen with no head chef. The control unit interprets instructions from the computer's memory and converts them into signals that can control other parts of the computer. It ensures that the right operations are performed at the right time. For example, it might send a signal to the ALU to perform a calculation or to the memory to fetch data. This coordination is essential for the smooth operation of the computer. Now, buses are sets of parallel wires that transfer data between different parts of the computer. They can have 8, 16, 32, or 64 lines. A bus is like a highway with multiple lanes where each lane can carry a bit of data. The more lanes or lines, the more data can be transferred at once. This is essential for the efficient operation of the computer. There are different types of buses in a computer system, each serving a specific purpose. The data bus carries the actual data being processed. The address bus carries the addresses of where data needs to be sent or retrieved from. And the control bus carries control signals that manage the operations of the computer. These buses work together to ensure that data moves smoothly and efficiently within the computer. The system bus is divided into three types: the control bus, the address bus, and the data bus. The control bus carries control signals such as read-write commands. The address bus carries memory addresses from the processor to other components, and the data bus carries the actual data being processed. Think of the system bus as a delivery system with three types of trucks: one for control signals, one for addresses, and one for data. The control bus is responsible for carrying signals that control the operations of the computer. For example, it might carry a signal to read data from memory or to write data to memory. The address bus carries the addresses of where data needs to be sent or retrieved from. This is like a delivery truck knowing the exact address where a package needs to be delivered. The data bus carries the actual data being processed or similar to the contents of the package being delivered. Control signals are essential for coordinating the activities of the computer. Examples include memory read, which retrieves data from RAM, and memory write, which writes data to RAM. There are also signals like bus request and bus grant, which manage access to the data bus, and the clock signal, which synchronizes operations. Control signals are like commands from a manager to workers, telling them when to start, stop, or perform specific tasks. Memory read and memory write signals are used to transfer data between the CPU and memory. When the CPU needs to read data from memory, it sends a memory read signal, and when it needs to write data to memory, it sends a memory write signal. Bus request and bus grant signals are used to manage access to the data bus. When a device needs to use the data bus, it sends a bus request signal. And when the CPU grants access, it sends a bus grant signal. The clock signal is used to synchronize the operations of the computer, ensuring that all components work together in harmony. The ALU performs arithmetic operations like addition, subtraction, multiplication, and division, as well as logical operations, as we can see, and, or, not, and XOR. It also handles bit shifting operations, which are used in various algorithms and data processing tasks. The ALU is like a calculator that can perform complex mathematical and logical operations quickly. For example, when you add two numbers in a program, it's the ALU that does the actual addition. The ALU is a critical component of the CPU because it performs the actual computations needed to execute instructions. Arithmetic operations involve basic mathematical calculations, while logical operations involve comparisons and decision making. Bit shifting operations are used to manipulate data at the bit level, which is essential for certain types of data processing tasks. The ALU can perform these operations quickly and efficiently, making it a powerful tool for processing data. The accumulator is a special register that temporarily holds data and results from the ALU. This allows for quick access and reuse in subsequent calculations. For example, in a series of additions, the accumulator holds the intermediate sums. The accumulator is like a notepad where a chef writes down intermediate steps of a recipe to use later. This makes the processing faster and more efficient. The accumulator is used to store the results of arithmetic and logical operations performed by the ALU. This allows the CPU to quickly access and reuse these results in subsequent calculations without having to write them back to memory. This speeds up the processing of data and makes the CPU more efficient. The accumulator is an essential component of the CPU because it allows for quick and efficient data processing. To execute instructions, the processor temporarily holds the current instruction, the address of the required data, the data itself, and the address of the next instruction. This ensures that the processor knows what to do next without any delays. Executing instructions is like following a recipe step by step, where each step requires specific ingredients and instructions. The CPU executes instructions by following a series of steps known as the fetch execute cycle. During the fetch phase, the CPU retrieves the next instruction from memory and stores it in the current instruction register. During the decode phase, the CPU decodes the instruction to determine what operation needs to be performed. During the execute phase, the CPU performs the operation specified by the instruction. This process is repeated for each instruction in the program, ensuring the CPU executes the program correctly and efficiently. Key registers include the program counter, which holds the address of the next instruction, the current instruction register, which holds the current instruction, the memory address register, which holds the address for data fetch or store, the memory data register, which temporarily holds data moving between the processor and memory, and the accumulator, which holds intermediate results. Registers are like different sections of a chef's workspace, each holding a specific item needed for cooking. Registers are small, fast storage locations within the CPU that temporarily hold data and instructions. The program counter holds the address of the next instruction to be executed, ensuring the CPU knows where to find the next instruction. The current instruction register holds the current instruction being executed, allowing the CPU to decode and execute the instruction. The memory address register holds the address of the data to be fetched or stored, while the memory data register temporarily holds the data being transferred between the CPU and memory. The accumulator holds intermediate results of arithmetic and logical operations, allowing for quick and efficient data processing. We have previously discussed the key registers included in the processor, but here we have a summary of which you might just want to have a quick look over again. The processor executes program instructions stored in memory, coordinated by the control unit, similar to how a conductor leads an orchestra. Each component must perform its role at the right time for the system to function correctly. Think of the processor as an orchestra, where the control unit is the conductor and each component is a musician playing their part in harmony. When the CPU executes instructions, it follows a precise sequence of steps. The control unit ensures that each component of the CPU performs its task at the correct time. For example, the ALU might perform a calculation while the registers store intermediate results. This coordination is essential for the CPU to execute instructions efficiently and accurately. The processor operates in stages to execute program instructions, repeating the cycle for each instruction. This cycle ensures that instructions are processed in a systematic and efficient manner. The fetch execute cycle is like a factory assembly line, where each stage performs a specific task to complete the final product. The fetch execute cycle consists of several stages: fetch, decode, and execute. During the fetch stage, the CPU retrieves the next instruction from memory. During the decode stage, the CPU interprets the instruction to determine what operation needs to be performed. During the execute stage, the CPU performs the operation specified by the instruction. This cycle is repeated for each instruction in the program, ensuring that the CPU executes the program correctly and efficiently. We can see that there are four main steps as part of the fetch stage. So fetching an instruction is like a librarian finding a book, which can be the instruction, based on its location, which is the address, and bringing it to the reading desk, which is the CIR. During this stage, the CPU retrieves the next instruction from memory and prepares it for execution. So the CPU retrieves the next instruction from memory and prepares it for execution. This involves copying the address of the instruction from the program counter to the memory address register, retrieving the instruction from memory and storing it in the memory data register, incrementing the program counter to point to the next instruction, and copying the instruction from the MDR to the current instruction register. Here, the blue lines indicate data flow during the fetch stage. This visual helps in understanding how data moves within the processor during the fetch phase. Visual aids like this can make complex processes easier to grasp. The visual representation shows the flow of data between different components of the CPU during the fetch stage. This includes the transfer of the instruction address from the program counter to the memory address register, the retrieval of the instruction from memory and its storage in the memory data register, the incrementing of the program counter, and the transfer of the instruction from the MDR to the current instruction register. This visual representation helps to illustrate the steps involved in fetch stage and how data moves within the CPU. Next, we decode the instruction. So decoding an instruction is like a chef reading a recipe. Understanding the steps, which can be the opcode, and gathering the necessary ingredients, which can be considered the operand. This step is crucial for understanding what the instruction is supposed to do. During the decode stage, the CPU interprets the instruction stored in the current instruction register. This involves splitting the instruction into its components. The opcode, which specifies the operation to be performed, and the operand, which specifies the data to be used. If additional data is needed, it is fetched from memory and passed to the accumulator. This step is essential for the CPU to understand and prepare for the execution of the instruction. In this stage, the control unit decodes the instruction in the CIR to determine the required actions. The visual representation helps to see how the control unit interprets the instruction and prepares for execution. The visual representation shows the steps involved in decoding the instruction. This includes interpreting the opcode to determine the operation to be performed, fetching any additional data needed, and preparing the data for execution. This visual aid helps to illustrate the steps involved in the decode stage and how the control unit interprets and prepares the instruction for execution. Finally, we execute the instruction. The instruction is executed and the result is stored in the accumulator or memory. So executing an instruction is like a chef cooking a dish according to the recipe and then plating it. When plating it is like storing the result. This is where the actual operation specified by the instruction is carried out. During the execute stage, the CPU performs the operation specified by the instruction. This might involve performing a calculation, moving data, or making a decision based on the data. The result of the operation is then stored in the accumulator or memory, ready for the next instruction. This step is where the CPU actually performs the work specified by the instruction. So to wrap up, let's review the key processor components: the ALU, the control unit, registers, and system bus. Can you name the 3 buses in the system bus? And can you name 5 special registers involved in the fetch execute cycle? These are fundamental concepts that you'll need to master. Reviewing these key components will help reinforce your understanding and ensure that you have a solid grasp of the material. These concepts are essential for understanding how a computer processes information and executes instructions. That's it for now, but thanks for watching, and remember to like, subscribe, and share. Bye for now.